Welcome to The Explainer. Every time you encounter a medical product, whether it's a simple syringe or a life-saving medicine, you're placing your trust in a completely invisible process. So today, we're going to pull back that curtain and look at the incredible science that keeps these products safe and guarantees with actual mathematical certainty that they are sterile. All right, so here's how we're going to break it down. We'll start with the huge challenge, that 1 in a million problem. Then we'll get into the specific language scientists use to talk about this stuff. From there, we'll see how a sterilization cycle is actually designed, how you prove it works, and finally, how you keep it working day in and day out. So, first things first, we really have to get our heads around the unbelievably high standard for safety in the pharmaceutical world. I mean, this goes way, way beyond just being clean. Yeah. Think about that for a second. How can you be absolutely certain? We're not talking pretty sure. We're talking about proving with hard data that there isn't a single living microorganism on something. And here's the tricky part. You can't test every single item to check, right? Because the test itself would destroy the product. The solution, it turns out, is all about probability and statistics. And this is the magic number. This is the gold standard. For something to be considered sterile, the chances of a single unit being non-sterile have to be no more than 1 in a million. That's it. For every million vials that come off the line, maybe, just maybe, 1 might not be sterile. That's the bar. And this target has a technical name, of course. It's called the probability of a non-sterile unit, or PNSU. You'll also hear it called the sterility assurance level, or SAL. Hitting that target of 10 to the minus 6, that's the whole point. It's the North Star that guides every single calculation and decision in this entire process. Okay, so to actually hit that 1 in a million goal, scientists can't just be winging it. They needed a very precise language, a set of tools to measure and predict how to defeat even the toughest microbes out there. And this is where we get into the real science of it all. So, meet the D-value. The easiest way to think about this is like a microbe's hit points, or its resistance to being killed by heat. It tells you exactly how many minutes, at a very specific temperature, it takes to kill off 90% of them. So a bug with a high D-value, that's a tough one to kill. Then you have the Z-value. This tells you how much deadlier the process gets when you crank up the heat. For a lot of microbes, the Z-value is around 10 degrees Celsius. What that means is if you raise the temperature by just 10 degrees, you make the process 10 times more effective, cutting that D-value by a factor of 10. It's a crucial little number. And all of that gets us to the F value. You can think of this as the total damage score for the whole sterilization cycle. It takes all the temperature changes over the entire time and boils it all down to one single number. What was the killing power equivalent to in minutes at a standard temperature of 121 Celsius? It's the ultimate measure of lethality. Now this is where it gets really clever. How do you know if your damage score is right? Well, you check it 2 ways. The F physical is what the machine sensors, the temperature probes, tell you happened. It's the theory. But the F biological, that's the proof. That's when you put a known number of super tough microbes inside and see if they actually died. And here's the key. For the process to pass, the physics and the biology have to tell the same story. All right, so you've got this scientific language. How do you use it to actually build a sterilization cycle? Because it's really not a one-size-fits-all situation. Depending on what you're sterilizing, you've got some pretty big choices to make right from the start. And the first big choice is your strategy. Are you going to go with the overkill approach? That's kind of like using a sledgehammer. It's a super powerful cycle designed to kill anything and everything, no questions asked. It's great for things like metal parts. Or are you going to use a product-specific approach? That's more like a scalpel. It's carefully designed for the specific microbes you expect to see, which is absolutely critical for delicate drugs that can't handle too much heat. Next, you have to think about what you're sterilizing. Is it something porous, like a filter or a bunch of rubber stoppers? The big enemy there is air. You have to get every last bit of air out so the steam can touch every single surface. Or are you sterilizing a sealed vial of liquid? Now your challenge is totally different. You've got to get the heat through the glass and into the liquid, all while managing the crazy amount of pressure that's building up inside that vial. So all that thinking leads you down a very clear path. For those porous items, you're going to want a pre-vacuum cycle that literally pulls all the air out before the steam rushes in. But for those liquid-filled vials, you need something totally different, like an air over pressure process that essentially squeezes the container from the outside to counteract the pressure building up on the inside. It's all about picking the right tool for the job. Okay, the math is done, the cycle is designed. Now for the most important part. How do you prove, really prove, without a shadow of a doubt, that you're hitting that 1 in a million target? The answer is a rigorous, documented, and intense process called validation. And validation really just brings together those two types of proof we talked about. On one hand, you have the physical proof. You put a whole bunch of temperature probes in all the hardest heat spots to make sure you're hitting your F physical. And at the exact same time, you do the biological proof. You place little vials of live, super-resistant bacteria, called biological indicators, in those same spots. In the end, what the probes say happened better match what actually happened to those microbes. And we are not talking about a one-and-done test here. A real validation requires at least 3 successful runs in a row. And you have to test the absolute worst-case scenario you can think of, the biggest load, the most packed chamber. It's all about making sure the physical and biological data line up, and using smart strategies like testing your biggest and smallest load sizes to prove that everything in between works too. But wait, the work is not done once you've passed the validation. Not even close. You can't just set it and forget it. A validated process is a living thing that has to be protected and constantly watched. And that brings us to our final and maybe most important piece of the puzzle, the ongoing watch. You really have to think of this as a life cycle. It kicks off with that big, intense initial qualification. After that, any change, and I mean any change, a new brand of bottle stopper, a slightly different way of loading the chamber, has to go through a strict change control process to make sure it doesn't break anything. And then, on a regular schedule, maybe once a year, you do it all over again. A full requalification to prove that everything is still in a perfect state of control.
You know, this whole system, from devalues all the way to validation life cycles, it's this silent, data-driven guardian that watches over public health. It's just a really powerful reminder that behind so many of the simple, vital things we count on every day, there's often this incredible, deep science at work, protecting us in ways we never even see.